Hi, Michael. Hi, Michael. Hey. Hey, Yannick. Um, I'm just kind of waiting here a little bit and see if anyone's jumping on. I guess this will be recorded too, so can always watch it later. Hey, Mouse. So I've never done this before. Well, I've tried Twitch in the past, and that has been not great. But I'm trying YouTube now for the first time, and just got set up with OBS Studio, and I hope I'm doing it right. I don't know. I sort of just went with the defaults pretty much and put up my camera here, and got a little rectangle in the corner of my screen, so that the text is big enough for you. So if things go wrong, like let me know because I'm a noob at this. Yannick, it's Sublime Text. It is a lovely text editor. It doesn't have a lot of fancy IDE functions, but for me, and I write in a lot of different programs, and I kind of tend to have just a few tools rather than like many specialized tools. I have just a few tools that are kind of generic. So this is what I use for all my text editing, like note taking, to dos, like programming, anything that I write that's text. This is what I use for. And this thing on the right side, this is iTerm. Open this about box for you too. It's very complicated about box, but so this is iTerm, item 2. I'm using macOS 10. Yeah, and that's pretty much it. And then for this project, which is on GitHub, and there'll be a link in the. Actually, let me just add that link into the YouTube, to the source code for this project, in case anyone wanna have a look as you're listening along. Let's see here. Can I just add it somehow to the video description? So give me a second here, just I think I have to. Okay, I'm just adding it to the description of the YouTube video. I don't know if it shows up live or not. Okay, I'm just gonna drop it into the chat. Anyhow. So anyhow, the tooling that sorry if I fiddle around a little bit. I have to just adjust my window so I can see the chat. Yeah. So Yannick asked about the coding environment. So again, recapping a little bit because I got distracted there. Sublime text, this guy here. iTerm over here. And then I'm using Clang as the compiler right now, but you can use GCC if you want. The reason I want to show you the source code is that this project is pretty small. It's pretty easy to get started. All you need is going to be Ninja or something Ninja compatible to run this, and Clang or GCC is a recent version of either of those, recent-ish. And some Bash compatible shell. I'm using C shell myself, but Bash will work as well. So you can just grab from the GitHub if you want to try this out yourself. There are more detailed instructions that I just mentioned in the README file, so that should be enough to get you started. Okay, I think we should get going. Previously, so this is the fourth part or episode of this season of weird programming / boring / amazing programming stuff. So fourth part, third part 1, 2, and 3 you can find on the YouTube channel. There's also a web page on my homepage that you can go to that has all the videos. You can download the videos if you want to watch them offline. Okay, so where we left off the last time was kind of wrapping up the instruction encoding for this kind of virtual machine instructions. And what I'm going to work on now in this fourth part is to recap. First, I'm going to recap a little bit the changes that I made since the third part. This is, 15 hours ago or something like that. It's a couple of small changes. And then we're going to have a look at 3 different ways by which we can evaluate or execute this code, right? Sort of like the actual virtual machine that kind of runs the code. So I hope that sounds good. I'm going to have a little eye on the chat here. Their thoughts on Dino. Yeah, Dino is super cool. It's cool that it has this function where you can just kind of bundle things together into a portable-ish executable. It's kind of cool. Let's see. Stream looks good. Thank you, iMatt, for telling me. Will this be a regular thing? Yeah, well, maybe it will, no matter the situation, at home. It's just nice to be able to, to speak with another office is usually in there. So it's a little awkward to, talk in the middle of the day if there's not a person here having meetings and such. Some more love for Sublime. That's cool. Someone regretting up being a big sir. It is JetBrains Mono. Yes. Maligi. I hope I said it right. Yeah, it is JetBrains Mono. I love it. I use it everywhere from Monospace Text now. It's super chill. Okie doke. I wish you guys that we can talk with each other. I think it's awkward. That's like this text chat, but it is what it is. Part 4. What have I done since part 3? So this project is about coming up with this little computer, right? Or this virtual computer, a little language for it, little assembly language for it, little virtual machine that can run it, something that's kind of portable. And just kind of quickly reiterate the project goals here. Primarily, it's just something I want to do because I think it's got to be fun and I want to, learn stuff. Secondly, I hope it can be a sort of substrate, sort of like a foundation that I can build other things on. Like I enjoy making like programming languages and compilers and stuff like that. And there's usually a point where you want to generate machine code or you want to generate some sort of target code like WebAssembly or whatever. And that can get kind of meaty. And it's really be cool if this could just be one of those targets. So you just make a little thing, anyhow. And in longevity, it would be really neat to be able to write programs, rich programs, like multimedia programs, not just text programs, that can survive a decade or two of bit rot. Like today, like I go and look at like a web thing, particular web things that I wrote just a few years ago, and they don't work anymore in like a modern browser. I'm like, okay, well, I'm just gonna stop maintaining them, right? So I think that there's some, at least for enjoyable software, for like personal scale software, for fun things. I think that there's real value in making that have a long life. So project goals. What changed since last time? There was a file with instruction encoding that we created last time. I decided that was just like bad, and I was sort of like going as my own advice actually, in a way to keep it simple. So I undid that. I just lifted all that back into the one header file. So there's just this one header file. There's this prelude file to this to find some like basic stuff because we're dealing with C here, but it's not project specific. So anyhow, so I lifted those in here. So there he is back into the one header file. Oh, hey Edward! Hur är läget? I hope you're doing well. So I did that. I lifted this back in here, and that was a good decision. Now there's just this one file to kind of care about. These little helper macros and constants, they've just sort of made their way down here to the constant section of this header file, and some of these function prototypes as well. Otherwise, there isn't much to do. So that was this to do point, right? So that's done. Then the second point, and this is what we're working on, or I'll be working on here in a moment, is to build an evaluator. Sorry, I'm listening to music, and like there's this amazing bug in macOS. It's long standing. I don't know if you guys. So this happens sometimes when you reboot your system. It just does this. But okay, let's get lower my music. I like that little music in the background. So we're gonna build this evaluator or executor for the virtual machine instructions. And last night, after dinner, I felt inspired, so I started putting together just a stub for that. And I think that's a good idea, because that saves us some time of seeing me just knocking out some boilerplate. So this is where I'm currently at, and this is where we'll keep going. Okay. So here we've assembled our little program, and on the right side here, if I hit save here, we can see it sort of like recompiling and then rerunning, and we see the output from our formatting function that we put together in the previous part. This shows us the instruction offset. So 0, 1, 2, 3, that's the instruction offset, or program counter if you were running this program. And here we have the instructions along with their arguments. Right, so we have a move instruction, and this implements a factorial function. It's a simple example here. Okay, now I'm going to show you what it looks like if we run this thing. So here's a new function that I wrote last night called eval. It needs some registers. So we just allocate those. There are 32 in this ISA, which is documented in the README file here. There are 32 integer registers and 32 floating point registers. None of this code using floating point, none of that. I'm not bothered with any of that yet, so don't need that. Anyhow, we just allocate 32 of those for virtual registers on the stack here, and we just pass those into the eval function along with the program. So this is the set of virtual machine instructions. And PC here has a different meaning down here. It's essentially just how many instructions are there in this array. And here we are setting up, so the register 0 in this ISA is the first argument passed along to a function. So if we look at this up here, factorial function, it takes one argument. So this will be in register 0, and it produces one output, which will also eventually end up in register 0. So before we call this factorial function, we need to set up its input arguments, and we do that here, and we give it number 3, and I think that should produce the result 9, I think. Let's see. Now this virtual machine is not, it doesn't work yet. We're gonna make this work, so this is not gonna be the correct result here. But we can print this out just for now. Oh god. Oh, that's what's that? There we go. Okay. So the output here is 11. That's not correct, I believe. Okay, now let's have a look at the way by which we could evaluate these virtual machine instructions. I should just comment this out. I think this is confusing for me. Okay, so here's some new code that you haven't seen before if you've been following along. There are generally, at least in my experience, now it's not like I'm a professional or expert of virtual machines. Like I've read about them. I've made some toy attempts at them and stuff like that. So by no means am I an expert here. But anyhow, what I've gathered, there are 3 general ways to just implement this in a programming language like C. The first one, which is the current one that we have enabled, is with one big switch statement. So now I got some macros here, so we can switch between the 3 without having to have a copy of the code. But so essentially what we're doing here is like we do switch, and then these are cases. So switch on the current operation, and then we do, if the operation is moved, then do this thing. If the operation is load I, then do that thing, and so on, right? It's just a switch case. The other way of doing things is with a jump table that has the address of like a chunk of code. So this would traditionally be what most VM implementations implemented in assembly would do. So you just build a table that maps, and we got one here, that maps the operation to some offset in code. So Clang and GCC allows you to do is super Yankee syntax, but like this basically takes the address of a certain offset in your code, right? Which is expressed as a label in C. And third, this is probably a more sort of like a less common thing to see in C, but just as effective in many cases. Similar to a jump table of addresses, you use a table of functions that just do tail calls. So for people into functional programming, you have continuation passing style, right? Where like instead of returning a value and using a stack to push pop on a stack, you call a function with arguments, and then that function, instead of returning, just calls the next function, it calls the next function, and so on. Obviously, if you just do that with a traditional stack, you push something and push something, if you do that enough times, right, you're going to run out of stack memory, you got a stack overflow. And so there is this optimization called a tail call, where at the end of a function, when you're returning from it, rather than returning, I should qualify that better. At the end of a function, when you're calling another function, rather than just like pushing on the stack, calling that function, right, and then returning and popping immediately, you can just say, you know what, we don't need this stack frame anymore because there's nothing else after this function call. So you can just pop the stack right there and just jump to that function. You don't even need to set up any sort of stack space for it. Anyhow, if you're curious about what tail calls are, go check it out and learn more about it. Anyhow, it essentially produces similar code. And I got a little setup here, and we're going to see what different code these will generate for x86. We can look at ARM64 too. Okay, so we got one big switched statement. That's the current strategy. We can just make sure that all of these work. So strategy 2 is going to produce a jump table. Now we get the same effect here. Kind of works. I've only implemented the logic for 2 instructions so far, which is the first 2 that are being issued in this program, and we can sort of hammer out the rest of them. So in the second strategy, what happens down here is that these, instead of these becoming case statements, these now become labels. So these are now transformed into, if we do this, these are now transformed into something that looks like this. There's labels, and essentially what will be added into the table is the address offset for this instruction right here, whatever this corresponds to machine code. And then our third strategy, and that code is a little different, so that is in the latter part of the file. So strategy 3, oh. Okay, look at that. So I broke that. That is lovely. Okay, let's see if we can quickly fix this so that we can have a look at this. TCTML. I just have a suspicion it's a station. Let's see here. So it's the address sentence, which is pretty neat. So what is happening here is BRZI. Oh. Yeah, this obviously is dumb. So I need to add some code here, and we got to see this in a minute here when we start looking at what code that the compiler generates for these different strategies. I kind of need to put something in here, otherwise the compiler is too clever and realizes that all of these do the same thing, and it can just sort of skip generating code for it, and it makes it harder to compare. So I'm kind of doing this to make sure that it's or something. So the instruction here gets too large and it overflows the space we allocated for registers. And so what we can do, we can just do modulus here, and we have